Burnt down. Dang. Anyway, the computer was working, but it was the backpack it was in was soaking wet, so I was surprised it's working, and now it's not working again. So, because the fire department put about 10,000 gallons of water in my house.
At least your grass will grow.
Yeah.
Try to find silver lining.
I know. I told my wife, I was like, you can get rid of those popcorn ceilings you didn't like.
Right. The Christmas tree that was in the attic, gone.
Yeah.
Holy wow. Oh man.
So it's picture showing time. That's my son's bedroom in the sky above it from the inside. So anyway, now I don't have a computer either, which sucks because I literally was on it today. You know, I was surprised it was working because there's literally water dripping out of my backpack. But apparently now it's gone. So, all right, let's talk about spanning tree. So on Wednesday we had talked about how to do discover switching tables so that we could be able to forward packets. But I made one major caveat in that, and I said that there could not be any loops in our network. Well, that's not very practical constraint because you may want to have loops. So you might want to have loops because you want to have redundancy. You might also want to have, or not want to have, but you might also have loops because of accidents. So if you have a big switching closet, it's not unusual to have a loop between two switches, even if it's by accident, right? So, and if you do that, even by accident, you certainly don't want to take down the entire network. And if you didn't do this, it would in fact take down the entire network, and we'll discuss why. So first, let's remember we had a network. We're going to do switching, so let's draw another network up here. So like let's have two parts of a building, right? And so we're going to network it here, 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 here. And so we clearly have a loop right here. Let's call this A, B, C, D, E, and F. So remember how did we discover switches last time? So last time we did it from a host level, right? So computer 1 is going to talk to computer 2 down here, which is on F. Right, so 1 talks to its switch, which is fine. That's totally uncontested because we're in modern Ethernet. And A builds a table, right? So let's say this is on port little a. And so we'll have, this is A's table. We'll have host 1, and it's on port little a. And then the switch just came up. The rest of the network just came up. So what we talked about on Wednesday, what do we do?
Broadcast to everyone.
We broadcast to everyone, right? So there's other hosts on this switch and they broadcast, but it's not connected to this switch. So eventually we do the broadcast thing, it's going to come out this port, right? And so then we would have, with our conventional, we'd have host 1 that wants to talk to host 2. Well, this switch doesn't know where host 2 is, so it broadcasts again, right? So it would go here, it would go here, it would go here, right? Out of everything that we have in the diagram. Now what happens? D receives host 1, wants to talk to host 2, doesn't know where host 2 is, so it broadcasts again. So let's say it's this packet here, right? So that packet there would go here, it would go here, and it would go here. Of course, this one came down also, so that would go here again, that would go here again, and it would go here. What happens to C? Yes. So this packet goes over here, good, and then it also goes here and here. A just got its message back, right? And then of course it happens on the same side, right? So it goes here, here, and then here, right? And then it goes again and again, and up and up, and again and again, back, right? So this is a packet storm. Because when we broadcast, we are duplicating that packet. And now the packet is being duplicated out across this loop. And it's spanning and killing the whole network goes down. Because remember what we talked also last week is that switches work on a buffer in a queuing system. And what do we do with packets that don't fit in the queue? We just drop it. So now the queues on the host and in the switches are dropping packets, right? So nothing could even communicate. So it's very possible that two can't even communicate into this network anymore because the buffers are totally full and it's just dropping packets. So two can't even say, hey, I'm over here. You can quit broadcasting these things. So the network goes down. So we need a way to fix this. So we could easily fix it. Notice if we're just looking at the network and we had like this big network picture, right? We could easily fix this. If we have the same network picture here, 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 and here, we could easily fix this by just killing out. And we no longer have a loop. But that requires us to have a large network picture. We have to know what our network looks like. So from the switches perspective, we want these to be plug and play, and you never, if you've ever bought a switch, you don't say, oh, there's 6 other switches in this network, and they're here, here, and here, and here, right? You don't do that, right, for the Ethernet level. You might do that for the IP level, but we haven't got there yet, right? So we want these to be plug and play. So what we want is, even though that this is here and this is here, we want to come up with an algorithm that could just automatically detect that. So if you were looking at this problem today and it was new, how would you go about doing it? Our constraints that it has to be fully decentralized. No switch can be the boss. There's no special switch, right? And you need to find a single one path through the network, and all of the switches have to agree on that path. So there's some things in our network right now that we might be able to use, right? So we have our network in alphabetical order, right? Which is essentially numerical order. So we could say, hey, we want to elect the boss switch, and we're just going to elect that by highest or lowest number. So let's just elect it by lowest number. So it would be nice if we could elect A, but of course we need to be able to find out where A is, and all the switches have to be able to do this. Even the switches aren't connected to A. Anything else we could do?
Just save a copy of messages that you sent.
So that's not a bad idea, except for we would like our switches to spend most time sending packets instead of looking at. So you're kind of like doing a deep packet inspection to figure out, hey, have I seen this before? If I've seen this before, then now we're possibly a packet storm. It could be a duplicated packet also, because we're going to duplicate packets on purpose later, right? For doing flow control, right? There's going to be duplicate packets on flow control. So, but that's not a bad idea. Not a bad idea.
Can you do like some sort of detect algorithm and then reset?
Sure. Let's do that. Let's do a detect algorithm. Let's send a special switch packet. Hosts don't send this packet. Only switches send this packet. Remember, we're playing fair. We haven't got into playing nasty yet. So we're gonna play familiar, and then we're gonna make a special switch packet. Hey, I'm a new switch, my name is A. Or hey, I'm a new switch, my name is F. Now, in reality, these numbers are not A, B, C, D, and F, right? They're very large, and they're unique. Ethernet has a specification that says every new switch that's being produced, and every host adapter for that matter, has a unique number, and that is the MAC address. And part of that unique number comes from their manufacturer part, a prefix to it, that every manufacturer has. And so Cisco has its own prefix, and then it has a serial number after it, right? And obviously a serial number is never duplicated. So those numbers are unique. We can depend on that. But for our demonstration, we don't need a 16-digit number, right? We just need A, B, C, D, F, right? Just to be able to order. So A could send out a special packet that says, hey, I'm A, I just came online, and I'm a switch, right? And F could do that. But we're gonna need some more information as well. What more information will we need?
Max.
Huh?
Maybe the max.
What do you mean by max?
The switch card, MAC.
Oh yeah, no, we're gonna say the MAC.
Okay.
So the
That's
A, B,
that.
C, D,
Okay.
E, and F is gonna be our MAC, even though it's woefully short. But it gives us an order.
Maybe connection. What's nearest?
Yeah, my neighbors.
Neighbor's neighbor, that's it.
Neighbors. So, and neighbors are gonna become important, right? We're gonna say, hey, we're gonna remember, we just get connected. And this algorithm actually works without even having, so a switch by the Ethernet standard can tell if something's connected or not. We're not even gonna use that yet. We'll use that later. So, and that's link state. So A could send out a packet that says, hey, I'm A, I'm new switch, but we might need something else. And I'm gonna propose to you that it's gonna be, hey, I'm A.
Ports.
Huh?
Ports.
No, A is gonna handle its own ports. So I am A, and I'm a new switch, and that's just the new switch part is because of this packet. And I'm gonna start out with a state. And that state is, I think I am the boss router. I am in charge, the root router. It's actually called a root. So, hey, I am A. I think I, A, am the root, and the hops to me is 0 because it's itself. Every other switch is going to send out the same thing. B is going to send out B, 0. C is going to send out C, 0, and so on and so forth, right? Now let's look at what happens. So the first round, everybody sends out its new, and let's just pay attention to C and D because they're the ones that are the problem children right now. We're going to have a table for C and a table for D. So first, right, our first one is going to be C, 0, and we're going to have a D, 0. Of course, C and D are going to send that out to each other. But A is also going to send out things, right? But so the first round, everybody just has their own state. Now, if A sent this out, C learns that A is the lower number. So in the second round, what happens? So C's state is going to look like this. It's going to be C, A, 1. Because it learns that A has a lower number than itself. Or more importantly, it learns that A has a lower number than what's in its table, which is itself. And so it's going to replace that and increment the hops. So now we have CA1. D would have what? By the way, C also gets that same packet from B and discards it because it doesn't beat A. So, but what does D look like?
DC1.
Huh? DC1. That's exactly what it looks like. So, and then in the third round, what does everything look like? Well, CA1 is going to stay the same because we are the omnipotent network gods. We can actually look and see that A is going to win, right? But we would know that if we were one of these individuals in the network. So A, this is going to stay the same, and then this becomes what?
DA2.
DA2. And I believe this network is going to need one more round for F to actually learn A, because actually, so first packet, second packet, third packet for F to learn. But then eventually, there's not going to be any more updates. Everybody's going to learn everything, and we will have a route through this network. We still have this problem because we just dealt with everything at the switch level. Right? So what do you do with that? We actually haven't solved any problem yet. So, but C would know when it's sending these out, and D would also know when it's sending these out that it's receiving 2 of these packets, right? These special packets. So it would do the same thing within itself on ports. It would kill this port, and it does that by lowest port number. And the port just turns off. So for automatic redundancy, so we put that there, one of the reasons is an accident, but the other reason is we want redundancy. Is what happens if this port actually dies? How does this one come back to life? And the answer is that we just repeat the process periodically. And D, at that point, for an algorithmic stand, D only needs to ask his immediate neighbors if anything's changed. And then if you throw link state in there, because the routers actually can tell if the link is alive or not, then it makes it even easier, right? But this way is what we come up, and this is called the spanning tree algorithm, and this is how we come up with a single tree inside of it. And it does. We could do the same thing if this thing was linked all over, and it looked like that. It would still work, right? There'd be a lot more packets being passed around, a lot more changes in the table, but it would still work. And now we can get a packet without a packet storm. We can do broadcasts and not have the packet storm we had before. We have a one-way through the network, and every single node learns this path. And there's some other things that they can use because they learn that path. There's some other things they can use to make their forwarding tables. So, if F wants to talk to somewhere on A, right, it doesn't need to store this whole state and recalculate it to forward it. It just knows it needs to forward it to D. Just like before. So that doesn't change. Our forwarding tables haven't changed. Right, this is just a way to build a sane forwarding table. So, at this point, we have covered Ethernet. This is basically all that you need to know, with the exception of wiring things together and soldering irons, how to build Ethernet. We actually have done all that, and we have a building working network. We can forward packets from A to F, or hosts on A to hosts on F, without any problem, and we can exchange information. And if we can do that, why on earth do we need, or not to the network layer, we haven't even talked about IP. Why do we need IP?
Because we'd have to map the whole internet.
We would have to map, that's exactly it. We would have to map the whole internet. How many computers are on the internet right now?
All of them.
Well, pretty much. But what in like an actual arithmetic-like number?
Isn't it billions by now?
It's well past billions. And my guess is, I think it's like 10 to 20 billion, right? So in this instance, if we have 20 billion computers on the network, our switching tables are 20 billion entries deep. That's not even the biggest problem. The biggest problem is every time a new computer comes online, we have to broadcast to the whole internet. We literally have to send 20 billion packets. Now, it's just that one computer sends one packet and it just starts replicating as it goes through the network, but we kill the network with the first computer that comes on. Right? 20 billion packets, and I don't know, I can't even fathom to guess on how many times computers can turn on and turn off every day. Literally, you forgot to charge your iPhone and you take down the internet just because it turned back on. Right? So it's not going to work. It's not going to work. Also,
So what's the limit on that?
huh?
What's the limit? What's the
Well-
recommended limit on something like that?
Well, switches are getting faster, but it's in the thousands, maybe tens of thousands, possibly. But this is why you start getting like layer 3 switches in your large organizations to take care of some of these problems. So these are simple switches, right? These are layer 2 dumb switches. We haven't got into management of anything yet. So by definition, a layer 3 switch is a network layer switch. So it's a switch with network IP functionality in it. So we can't turn off the internet just because we have a bad design. It doesn't scale, right? There is definitely a way, and it's very useful, right? So this way, right now, we don't need IP, and there are things that work locally that don't use IP. So if you turn on your computer, right, and you attach to a network that you trust, then, and you go to print and you don't have a printer, it will say, hey, there's this printer here and that printer there, right? None of that's IP based. That you don't know the IP address for the printer, so how are you learning that information? And you're learning that information on the link layer. The other problem that we have is we designed one network. And we've also talked about wireless last week, right? The link layer protocols are not the same. So we have no way of taking if this was a Ethernet, right, and we're going to attach it to wireless, this doesn't work, right? We need another layer on top of it to be able to do translation, to go to a different link layer. So we want different link layer technologies to be able to adapt and evolve into more efficient, more robust networks. But every time we do that, we don't want to have to replace the entire internet. So we need to be able to grow these things in isolation and then have them connect, right? So we would need to have this look like, okay, this, right? And then we have some other thing here, and we need some way to connect it. Even if this is just Ethernet and Wi-Fi. Now, Ethernet and Wi-Fi, this is really just a box, right? That sits here. It's called an access point. And in most houses today, this might also be your cable modem. Right? But inside of that box, you're still having to do all of this stuff. The Ethernet protocol, the link layer protocol for Ethernet, has a fixed 1500 byte packets, right? Where Wi-Fi has variable length packets, right? So you can't send those packets across. You need to be able to translate back and forth. And we also need to solve the scaling problem, which is how do we make all of these clouds interact with each other? And at the same time, we would also like to be able to fix this. We would like to have multiple paths through the network. So, and one to actually, you know, if computer 1 is talking to computer 2, and this happens to be, you know, a third of what this is, and this is all Ethernet right now, but imagine we scale this out to an actual inter-network, right, with multiple different networks. We have different, because there's different link layer technologies, there's different bandwidths between the two, and there might be different loads between the two. And so we would like to be able to spread that across. So sometimes when A talks to, 1 talks to 2, sometimes it goes C, D, and F, and sometimes it goes C, B, and then F. We'd like to be able to do that, to spread out the bandwidth, utilize our network. So what are some of the strategies for that?
Kind of like OSPF and RIP and.
Huh? So we haven't even talked about building tables yet. So we're gonna magically build tables, and then we'll talk about how to algorithmically build them later. But for right now, imagine you could just be the network god for a moment, and you get to look at the internet, right? How do you, if you were going to build a table anywhere in that place, what strategies, what things would you want to consider?
Bandwidth and distance.
You want to do bandwidth, right? And distance, which usually translates to latency. Later on, you're also going to want to know about money, because you might have something that is close and very high bandwidth, but it costs a lot of money to use. Because I guarantee you, if you're willing to dig a trench out there and bury fiber, you can get a lot more bandwidth than you can using the Wi-Fi, right? But that costs money, and even if you lease that fiber, you're still paying for it, right? Just over the long term. So we're gonna consider bandwidth. We're gonna consider latency or distance. We're also gonna consider money, and we're gonna consider load. And we're gonna build on this for like the next, probably at least 2.5 weeks. Because it turns out it's super complicated. But we could come up with some strategies. First, right now we have a haphazard network. Right? We throw these things together, we connect stuff in the building, there's no planning, it's fully decentralized, blah, 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 blah. So we're gonna change that, and we're gonna put a little bit of management on it. We're gonna say, hey, everything in that network, that building, is under an IP address range. Right? And then those IP address range are in a hierarchy where if you want to find anywhere to go on the internet, there's a hierarchy that you can go up and eventually come back down in a tree. Right? And that's how IP addressing. So we're going to talk about IP addressing. We're going to talk about actually doing forwarding. So it turns out there's quite a bit of stuff you need to think about when you're just forwarding a packet. Right? And then at the end we're going to talk about routing, which is how to build the tables to do forwarding. So routing is a large, arduous process that doesn't need to happen every single time a packet goes through a switch. Right? It's a discovery process that needs to be done periodically, much like our spanning tree, that builds a table that does forwarding. The forwarding has to be fast, because how many packets are going through one of the core routers in Denver? Right? It's millions upon millions every second are going through those routers up there. Millions and millions every second. Right? So that has to be a fast process. And so we'll talk about actually doing forwarding and making that work. And then at the end, we'll start talking about loads. Because we might find if the network was unused, if the entire internet was unused, we'd likely find we could definitely find the best path through the network. We just ignored everything else. Of course, everybody else in the world, if we design our algorithms correctly, is going to find the same exact path. Right? And then we're all going to try to use that path at once, and it's going to die. Right? So what we want to be able to do is to switch paths when the load starts getting high. And we need to design an algorithm for that. How to do loads. And even if we do choose the same path, we all magically choose the same path in the network in this classroom, we need to figure out a way to throttle each other back fairly so that we can use the network efficiently and not kick everybody else's packets off. Because if we were all just jealous about it and use that network or not just selfish about it, and we just use that network as we pleased, right? All of our packets, even mine, even if I was the one that was being selfish, would go to the bit bucket, and nobody would get to transmit anything. And then all that will go into the last part of the class, which we start talking about quality of service and security, which is quality of service is doing everything fairly, or at least paying for everything fairly, usually. And the security is, how do you kick the bad guys off, the guys that are cheating? How do you locate those guys and not necessarily kick them off, but send their packets to the bit bucket and not everybody else's. Any questions on the link layer? So this class is going to we did a whole lot of engineering, electrical engineering type thought at the beginning of the class. This is the point where we now, well, we use some of that information, particularly the bandwidth delay product, to choose paths down the network. We're going to translate now into much more of a computer science. Like, this is going to be a lot of algorithms. All right. Sorry for the short class. I really had zero time to prepare. On Friday, I slept 45 minutes Friday night. The fire department left my house at 5:45 in the morning.
You had a fire?
Oh yeah, burned the whole top floor of my house. Toast. I talked with the insurance adjuster guy, and he said something that just made me cringe. He said it might have been cheaper for your house to burn all the way to the ground and just start over. He's like, and that would have been because like the house replacement cost was $487,000.
What was the root cause?
We think it was the heater in the lizard cage, or on the lizard cage.
Malfunction or user error?
Cat error. Well, it might be user error in the dumbass engineer that designed it, i.e. me, didn't like weld that thing to the.
That's something almost happened in my house, actually.
Really?
Yeah, I have a bearded dragon, and the
So did he.
there.
Yes. So he had a ceramic heating. So he has the basking light and the UV lights. Those were off because they're on a timer. They just turn on and off with. Turn on in the morning at 6 a.m. or 6. They turn on at daylight, turn off at 9. But there was a ceramic heating element that kept the lizard warm at night. It's not usually a problem. They don't usually need that. But he's been really sick for like the last 3 weeks, and the vet said try to keep the cage at 80 degrees, even at night. And so there was this heating element, which is kind of like, it screws into a light bulb socket, but it's not a light bulb. It's basically a little heater. And it turns on when the cage gets below 80, and of course, if a cat knocks it off onto the floor, it's not heating the cage, but the thermometer is still turning it on.
For my light, the cat knocked it, same thing. Cat knocked it off the thing. The bulb of the actual light bulb, like that shattered, so it was just an exposed heating element, perfectly like sitting on my hardwood floor. So now I have this big crispy ring. That luckily I was home, but I was able to smell it burn.
I have a very large crispy wing brain.
Yeah.
Like a 1,200 square foot one.
That really sucks.
Cat make it?
Huh? The cat made it to screw me another day. Yes, the cat made it.
Besides,
The lizard did not make it.
Weird.
But the two dogs made it, and it was date night for my wife and I, and we were not home when it happened. The kids were home. So my 15-year-old was the one that called 911 and drug Joey out of the house and the dog out of the house. The fire was already coming out of the back window, and things were falling down on the deck, so the deck was on fire, and the kids had to run through the deck and drag one of the dogs through it. So I got the call from the sheriff's office. We were like 2 blocks from home, and my cell phone rings. And I'm like, who is calling like this hour? And I was looking at the number. I was like, that number's super familiar. You know, because I used to be a cop, right? And I'm like, oh my God, that's the sheriff's office number. They're calling my cell phone. That ain't good. You know, it'd be one thing if it was a buddy, but if dispatch is calling you, so you see 390-5555, I'm all, oh, and so I answered it, and they're like, you know, they go through the routine, identify who you are, and there's like, your kids have called 911. I'm like, okay. So then I was thinking, oh, well, you know, maybe it was a misdial, and the next thing they say is your house is on fire. And I'm like, I am 2 blocks away. So I beat the fire department there. And the kids were in the driveway, very distraught. And I could see the glow coming out of the back of the house, but I couldn't see the fire over the peak of the house. And I opened up the front door, and it was like 500-degree oven. So I just closed the front door. I was like, yeah, I'm not going in there. So then I went around the back of the house, and the flames were taller than the trees. So it was like 20, maybe 30 feet high. So it was really long. It seems like it happened 6-7 days ago. That's how long my days have been. I don't even know what.
Trauma slows the world down, right?
Yeah.